Okay. I think now it's recording. Okay, so yep.
So I have a question.
Mhm.
So can you also please upload these recordings somewhere?
Yes,
Same
I
as
think I'll do
lectures?
today. Yeah, sure. I can give you the file, or I can upload to YouTube and give you some link, and you can watch there whenever you want, as you prefer.
It doesn't matter.
Okay, YouTube. I to keep it like a backup there.
Okay, thank you.
Also easy to share. Okay, so okay, so we were doing well, we were analyzing this charge sensitive preamplifier. I think last time one was not quite prepared to this, and now I do, I think. So the charge sensitive preamplifier, basically what it does is accumulate the detector capacitance and do the integration from the detector capacitance to a feedback capacitor connected in a feedback loop of the op-amp circuit. So basically, the detector capacitance is the capacitance for the detector combined with the stray capacitance that the cables may have when we connect the detector to this preamplifier. And okay, and basically this is an integration circuit with some gain. We have some voltage output, which is correspond to some charge integrated from delivered by the detector. So um, well, what we have here is the one key characteristic of this circuit is that the charge in the feedback capacitor it's almost the same or the same as the charge generated by the detector. No, it's one of the requirements for this to work. So one of the advantages of this configuration is that the charge amplification only depends on a well-controlled component, which is the feedback capacitor. Later on, we will see what is the difference and the dependence on the capacitance of the detector, for example, in amplitude configuration for an amplifier. So the okay, so the charge in the capacitor and the feedback capacitor is proportional to the original charge from the detector, this one here. In this configuration, it's essentially a charge integrator. And with some gain here, no? This is for an example of an inverted amplifier charge configured amplifier. So to understand this, we have to take into account well, remember some basics things about the op-amps. We in an ideal op-amp, we have that the internal impedance of this device is we consider it as infinite, so it's very large. Therefore, the charge from the detector will be the same as in the feedback capacitor. No? So the charge accumulated here will be the same as the charge delivered by the detector. That means that the voltage output will be proportional to the charge in the feedback capacitor divided by the capacitance of this component. No. And that means also that the charge from the well, the voltage output will be proportional to the charge from the detector divided by the capacitance of the feedback detector. So In both cases, we have the voltage output is dependent on only on the capacitor in the feedback loop. Okay. Okay, this configuration has an amplification factor A. Is actually is minus A. It's like an inverting voltage sensitive preamplifier. So we will have some voltage output, which will be equal to a negative amplification factor multiplied by the voltage from the detector, which is this one here. So the voltage of the detector is well, this is the kind of an ideal model of the detector. And we will have some voltage from this part. And so the voltage in the output will be equal to the detector voltage amplified by a factor minus A. So, okay, so if we see some mesh analysis of this, well, electrical analysis of this circuit, taking into account that this impedance on the preamplifier of the op-amp is very large. We have that the voltage in the post inverted and not inverted outputs is equal to 0, the difference on voltage. So we have no current here. So the equivalent circuit is something like that. So we have that the voltage from the detector is equal to the voltage from the feedback capacitor times the voltage in the output, which is this one here. Then we can substitute here the voltage output by this equation here, replacing, well, and then we can get this, well, factorized here and get the voltage in the feedback with respect to the voltage from the detector, no? Okay, and using also that the charge is equal to the capacitance times the voltage, and substituting and making the substitution in this equation here, this voltage from the feedback and voltage from the detector, we get that the charge from the feedback loops divided by the capacitance of the feedback capacitor is equal to the amplification factor plus 1 multiplied by the charge from the detector divided by the capacitance of the detector. So, and also, well, since the charge in the input the charge in the input of the op-amp, it's equal to the charge accumulated by the feedback capacitor, we will have then that the capacitance in the input will be approximately equal to the capacitance in the feedback loop times this amplifying factor times 1. So, and yep. So, well, and this capacitance input is called the dynamic capacitance, which is generated here in the input from of the operational amplifier here. So at the end, the charge amplification of an inverter amplifier configuration per unit of charge, it'll be the change in the voltage in the output with respect to the change of the charge in the input. That will be the amplification factor times the voltage in the input divided by the capacitance in the input times the voltage in the input. So, and we will have this that the amplification factor per unit of charge will be equal to the amplification factor of the circuit divided by the capacitance the dynamic capacitance in input, which this one is well we got from here. And at the end, we have this amplification factor divided by the amplification factor times plus 1 multiplied by the capacitance of the feedback capacitor, this one. So this will be the gain of the circuit per unit of charge in the input. So we can, for example, think that well, normally the amplification factor here will be very larger than, well, much larger than 1. Normally, we want to amplify the inputs, and at the end, um, the amplification factor will be dependent on the capacitance from the feedback capacitor, this one. Okay, so then we have another parameter that is that we have to take into account, which is the charge transfer efficiency, which basically is the efficiency of the charge transfer from the detector to the feedback capacitor. So so for a perfect or 100% efficiency, we want that the charge from the from the detector is transferred to the feedback capacitor. So, well, how is defined this transfer efficiency is defined by the ratio of the charge of the feedback capacitor divided by the total charge of the on the system. So, and what the total charge is the charge of the detector. That's the charge in the detector, plus the charge of the dynamic capacitance. These two are different things. So this one is the charge that the detector is generating, but this is the charge that is actually in the input of the amplifier. Then so well, that means that the large input effective capacity. Let me see. Okay, so this let me see, what is the large capacitance? Okay, so we have a concept here, which is the dynamic capacitance or effective input capacitance, which basically is the capacitance from the input or the dynamic capacitance is the charge in the input divided by the voltage in the input. This will be the same as the capacitance from the, well, will be equal to the capacitance from the feedback capacitor times this thing, no? So what is the total charge fraction that is measured? So this is basically uh, 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 this is what we, okay. Let's see. Okay. Well, the fraction of the total charge measured is the charge in the input of the amplifier divided by the charge from the detector. Oh, the total charge, sorry, this is the total charge. So the charge in the input is basically the input capacitance times the voltage. So this part here. Then the total charge is we saw this thing here. And well, we do some algebra here, and we get that we can get to this that the well this ratio depends on the capacitance of the detector and the capacitance of on the input. So to get the this well we want to have this ratio to be one. These ratios of to get this we want the capacitance in the input to be larger, much larger than the capacitance of the detector. So in this is a parameter to take into account to get a good efficiency on the transfer of the charge from the detector charge from the detector capacitance to the capacitance in the input from the amplifier. No. Mhm. So any question up to here? So maybe it's confusing a little bit or not? All fine. Okay. Okay. So okay. Well, we saw that what we have basically with this in charge sensitive configuration is just an integrator, a simpler integrator circuit, which at the end will deliver a step function depending on the shape of the voltage in the input of the amplifier. So that will give something similar to this. So we will have some current or pulse in the input of the amplifier, then the circuit will integrate this pulse and we will have some output like this, no? We some voltage level which correspond to the signal in the input, of course with some gain. But we can also use modify this configuration to to generate a pulse in the output. So one of the simplest way to do this is to add some feedback resistor, which will provide a decay time which depends on the values of this feedback resistor and and the feedback capacitor. So this well, and then we will have something like that, no? Some input pulse that will create this integration part of the signal, but then it will decay in an exponential function. So the voltage in the output at the end will be equal to the charge of the in the feedback capacitor divided by the capacitance in the feedback times this exponential equation, which depends on the time that will represent this charge of this capacitor um, with depending on the values of the resistance and capacitor array in the feedback loop. So which basically is this tau in the feedback. So well, and this resistor capacitor array can be choose according to the requirements from our system that we have. Okay, so we see here that we have there are two possible configurations to couple the detector to this amplifier. One is the AC coupling, and the other one is the DC coupling, which the AC coupling basically have a coupling capacitor and at the input to remove the DC component from the signal from the input, which is something like this. So we will have only the part that fluctuates with the time here. And the other one is just DC coupling, which keeps the offset, like we can say like offset or DC component to the input to the amplifier. Okay. So questions here? No. Okay. Okay. So there is one of the characteristics of this resistive feedback mechanism is that depending on the rate of the we are measuring with the detector, we could have a pile up, which this will come at high when we are measuring on high rate. So well, of course, that will depend on this factor that we choose of the resistor capacitance array in the feedback loop. This looks like that. So a low rate, shouldn't be a big problem, but a high rate, the signals will overlap with the previous signals that we might find in the input of the amplifier. So one of the mechanisms to avoid that, well, to improve, this technique can of course work low rates, but if we want to work higher rates, for example, there is a pulse reset mechanism which what it does is forcing at certain time to discharge quickly the feedback capacitor using some switch. Normally, these switch are some transistors which make able to well some transistor. I think we saw something at the beginning. I will go back a little bit. Um, transistor. Yeah, something like this. So we can put some poles and then close some circuit, which is a switch made of a transistor, for example. So some circuit like that, we can put some control with some other device, this switch, and discharge as we desire the feedback capacitor. So this is very well. Is a good way to control this the discharge of the feedback capacitor. So well, this normally we do with some logic. In the next slide, we will see a real life example. So well, this has to be designed according to the needs of the detector, but one typical use is to have the detector input with the switch in the feedback. The feedback here well, the feedback switch, normally we keep it open. When it's high here means that the circuit is open. So in the output of the preamplifier, we are basically, well, we are integrating the signals that are coming into the amplifier. So we see a ramp in the output of the of the of the of the charge accumulating in the capacitor here, in this capacitor, while the detector charge is decreased because it is being transferred to the capacitor, the feedback capacitor. So, and then when we close this switch, the this capacitor is discharged, so we see a quick a ramp to discharge the capacitor here, and so we have a ramping down time here. But the detector cannot acquire any charge here. During this, well, this phase here is called the reset. This is the reset time. So when we have the reset time, the detector cannot deliver any charge to the capacitor here, and any signal that is coming at this time is lost. So we don't see any input here. So this is kind of a dead time. But this can be solved using an extra switch from the input here in the source. This switch will disconnect the detector from the amplifier array, and what it will do is allow to the detector to charge independently of what the integrator is doing. So if we see in this time diagram, we have again the same scheme as here, that the preamplifier output is charging while the detector is transferring the charge to the feedback capacitor. But when we want to reset this capacitor, we disconnect first the detector from the input, and we have some time here, some short delay time before the discharge, but the detector can still charge itself from these signals that are coming when we have the reset phase of the capacitor. So first we disconnect the detector, then we close the reset switch, and then the preamplifier, the capacitor is discharged, and then well, the detector is being charged from wherever is coming into it, and then we can continue with integration. So this reduces the time of this using this mechanism. Okay. Okay, so well, this is a real life example and how an integrator is used, and also is using the pulse reset mechanism. Well, this also combines two integrators to reduce as much as possible the time, and basically is not the time. This scheme is used for some detectors in ALICE, so B0 detector, for example. So is how it works? Well, this scheme was designed to have one integrator assigned to every bunch crossings from the interaction well, we have bunch crossings every 25 nanoseconds in LAC, so we have collision every 25 nanoseconds. And we have assigned one integrator to work in one bunch crossing, and another one to the next bunch crossing. So they are alternating to work in different bunch crossings, so to reduce the daytime or get rid of it. So this is basically the same scheme, so with the reset switch in the feedback capacitor, one assigned for each bunch crossing. So we have one input which is going to the inputs of the two integrators. So when one bunch crossing comes, the if first integrator is working, do the integration time, and it's stopped at 25 nanoseconds when the second integrator comes to work. And in the meantime, the first integrator is doing the reset procedure, and so on. This is alternating, and each of them have also his own ADC, and this provides the information of charge for every bunch crossing. No, we have this for example a time scheme and how it works. So we have the first integrator with some integrator gate where the pulse is coming for this bunch crossing, integrating, and then it perform the reset of this integrator, while the second integrator is doing the work of doing the integration, and then reset while the other one is working, and so on. No, and this is the idea behind this technique. So any questions? No? Okay, so then we have also a current sensitive amplifier. This is not well, this is simple when once one understand the voltage sensitive. At the 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 idea behind this current sensitive amplifier is that at the input simply has a current to voltage converter, and at the end the work principle of the current sensitive amplifier is the same as the amplitude sensitive amplifier. So here what we have is a resistor which is in parallel with the current source from the detector, and with the inverted and not inverted input, which convert the current from the detector to a voltage level, well, that then after it's amplified by the circuit, no? And that's how it works. Okay, we don't need to get into deep here. So any questions here? Okay. Okay, so okay, so then well, this is basic concept. I think you may know this. Is I will go quick over this, which is some concept of the what is signal to noise ratio. Basically, this signal to noise ratio is the how much bigger is the signal that we have with respect to the noise level from one input that we have. So, and what we want from this is to improve the sensitivity of the detectable signal, the minimum detectable signal that we have in our detector. We want to have a much larger signal with respect to the noise. Here, the fluctuation from okay, so we have the signal that we have here depends on the fluctuation due to physical detection processes. For example, energy position or other detector readouts, things like as a photomultiplier. But also we have some contribution from electronic noise, which can be due to thermal noise, for example, which change the velocity fluctuations in charge carriers, shot noise, which are fluctuations in current numbers. For example, diode barriers crossing an iterated circuit, dark noise, and etc. Many things can be so. Okay, how this looks. So we have the case where, for example, we have some baseline, some signal which has larger level than a baseline noise. Well, and basically we have some signal at the end that which is dominated by the signal distributions, and in the case when we have very large noise, so when at the end we will have some distribution which is dominated by baseline signal, so signal will be very difficult seen in this case. So we want to avoid this situation. So okay, so say that we have here a comparison or how an amplitude amplifier is affected and is dependent on the capacitance from the detector for this signal to noise ratio. So for a voltage sensitive preamplifier, we have a given charge from the source, from the detector here, and which delivers some voltage of the signal, which will be this voltage signal will be the charge from the detector divided by the capacitance of the detector and the input capacitance, which is these two capacitance here. And we can assume that we have some input noise, so some voltage level of noise. And to get this signal to noise ratio, we introduce this equation here. So, and we see that wait. Okay, yes. We see that we have some influence from these signals to noise ratio, which is dependent on the capacitance of the detector plus the dynamic capacitance from the input here. So we can say, or we can conclude that the signal to noise ratio is inversely proportional to the total input capacitance. That means that the lower is the capacitance, the best is the signal to noise ratio. So for this voltage sensitive amplifier, we always want to have as low as possible capacitance in the input of the amplifier. So okay, and from here we have this, we see this dependence, no? And okay. And okay, so well, and we see that, for example, for charge sensitive capacitor, we the dependence on the output is with respect to the capacitor, feedback capacitor. So, and we have this parameter well controlled. While in this case, for example, at least the capacitance of the detector is quite can fluctuate a lot depending on the, of course, depending on the technology. For example, some resistive plate chamber or wire chambers or something from the construction, channel to channel or module to module, this capacitance can vary a lot. So that will imply an extra effort for example, for calibration. So you have to somehow compensate these differences on the capacitance of each part of your detector to have a consistent performance on a many channel detector. So that's is kind of a disadvantage that you can face when you have this configuration. And with charge sensitive, well, you have a better way to control this part of your readout chain. So, any questions here, confusions, anything? Oh, okay. Okay, well, apart from detectors, one thing that we have in the middles or and everywhere is cables. So this is also an important thing to consider and know what happens when we add certain types of detector or cables on our system. So that also can influence the performance. Uh, so um, the cables is the mean where we transport our signals. So we have to take into account what are the characteristics of the cables that we use. Here we will see, well, just this one as an example, as a case of how we can understand and study this part of the system when it's needed. For example, well, the the cables have a resistance, which is based basically on the length of the cable, the cross-sectional area, and the resistivity of the metal. So there's a material dependence and also a geometrical dependence of the type of cables that one will use. So, and this will represent a voltage drop along the cable. That will depend of course, on the length and the type of material we are using, and the geometry. So that's some things that we can look when we want to design something which is very specific characteristics. So this is an example of a standard coaxial cable that is very commonly used at CERN. And we can find the basic properties in data sheets, for example. So this is for example, this is the resistance of the inner and outer conductor, the speed of light, even the speed of light the speed of the signals in this cable, the impedance, the characteristic impedance at certain frequencies, and the operating voltages that we can use with these materials, no? So that's things that sometimes we are interested to take into account, and sometimes it's an important part to to check. Well, also the cables, this at least for this specific example, depending on the characteristics of the cable, we will have some impedance of this type of cables, which for a coaxial cable is we can represent this behavior as a array of coils, resistance, and capacitors, which basically we will add this inductive impedance, the resistance impedance, and capacitance. So, and that it's modeled with these equations. You know what are these equations that we see here? You remember from where are coming from? From electromagnetism courses.
More or less, yes.
Yeah, from where?
They come from the geometrical, how do you say it? From the cylindrical
Yeah.
geometry of the cable.
Yes. Well, because it's from this geometry, which is coaxial, and the cylindrical geometry, so it's like is that, no? So the capacitance, well, the impedance due to the capacitance and the inductivity comes from the geometrical shape of the cable, and also taking into account, of course, the permittivity and permeability of the material. And from here, we can calculate the impedance due to the capacitance uh, and the inductance of this cable. And this also define the the speed of propagation of the signal in the cable. Okay, well, this is important because, for example, for slow pulses, the cable has like a simple conductor, no problems with that. But when we are working with fast pulses, then we can see considerable changes, which can become important. And then one has to work on this part, no, to take into account seriously these cables for to have a good performance in case of need. Okay. So I think this will be the last part. So, well, in the readout chain, we have another part from after the amplifier, we have filters and then shapers. So we'll see part of it. Okay. So up to now, we saw only, well, I put emphasis on the charge sensitive amplifier, which if most of the charge sensitive amplifier can, well, for many applications they just give the at the end something as a step function. So integrates the input and we will have some step function. But we saw a technique in how to convert this into a pulse or something to discharge and take another pulse from the detector. But this step function or this level from the integrator can also be shaped to make more manageable the work with the signals, no? So we can expand the pulse to some very thin or small pulse to some shape that is more easy to analyze or or to analyze, yes. So um, this is done using shapers, which are an array of low pass filters and high pass filters. And that, for example, the low pass filter is used to improve the signal to noise ratio and work with the fast component of rising signals of the in the input, so that that will make the signal broad. So and the high pass filter will avoid or will control the width of the output signal. So and with these two components, we can have control of our output signal. So this is the more or less the chain. How can we visualize this? So we have the detector here with some current integrator, which is the charge sensitive amplifier. At the end, as I said, this input can generate some, we can say a step function, which from the integration. And then using the high pass filter, we take, actually a differentiator, which is take the derivative of this pulse. So take just the rising edge of the step function, then increase to a peak and then decay at with certain decay time. And the second stage, which is the integrator, is make smooth the decay time of this pulse, and also shape the can control the width of this pulse that we have at the end, no? Okay, so if we analyze a bit this with a very simple passive filter circuits, so we have the differentiator or the high pass filter here, which is an array of capacitors and a resistor, which will convert the step function from the integrator to something like that, and the equation that represent this is basically the energy or the voltage in the output will be equal to the voltage from the step function multiplied by the exponential by an exponential with a decay time defined by this resistant and capacitor array, which is this part here. And similarly for the integrator part, which basically, well, what it does is changing the array to pass the low frequencies, and then that will yeah, will generate an smoothing. Will do an smoothing effect from the step function, which is it can be represented by this function. No? Okay, if we combine these two with the amplifier, we can have something like this. So here we have the high pass filter, which with decay time, let's say decay time tau 1, that depends on the capacitor and resistant array, and a high pass filter also with a decay time depending on the resistant and capacitance array from the in integrating part of the shaper. So
it's called the time constant, no?
yes, time constant. Yes, time constant. I think it's a better word for this. Okay. Yes, this time constant. So and using this time constant, we can get different shapes. So we can basically modify the shape of the pulse as we need. The choosing these values for the low and high pass filters in the shaper. Okay. Okay, well, just as extra information of these filters, there are many ways to design these low pass and high pass filters. And this we have, for example, RC arrays or LC arrays or LR arrays. So well, we can choose the different configuration, combining resistor, capacitors, and coils. And the same for high pass filters. So we have these three types of configuration for the two types of filters. And one thing to take into account is the cutoff frequency for these two arrays, for these two filters. And so we can calculate at which point the voltage in the output, let's go back a little bit, the voltage in the output here of any of these two arrays will be reduced by 3 decibels. So well, this is a convention. 3 decibels is considered the cutoff frequency of these filters, and this we can calculate using this formula here, which is basically the inverse of 2 pi multiply the resistance and the capacitor of the array. Well, this is for resistor and capacitors, yes. And yes, so this will cut off the level of the output with respect to the input at 3 decibels. So this some design parameter that we can calculate. Okay, and okay, this is just a bus. I think we can skip that. This is not important. Well, this is just a band pass filter, which is just it's a circuit we can reject or select some specific bands or frequencies at the input. So, for example, if we know a specific range of noise that we will have in our system, we can introduce something like that to reject these exact frequencies. Or if we have some frequencies which we expect from our detector or our system, we can create like a window of frequencies to let pass in the output only those frequencies. And so like or make a selection of frequencies for any purpose we could have, no? Okay, so questions up to here. We are going to another topic. What time is it? What we have here? We can keep this for the next class. Is some fraction, some fraction. I think we can do this and we'll finish. I think. Yeah. Okay, so I think we see well, I explained already this in when we saw the application of operational amplifier, which basically is a pulse discriminator. And I think we saw that. So this is all lecture, but just for you to remember. Let's go back a little bit. Oh, here. Yeah. Okay, yes. Okay, I forgot what it was. Well, okay, these comparators. Give me a second. Forgot already. Uh-huh. Okay, pulse discriminator. Okay. So this pulse discriminator is basically an array of what is it? Of these comparators. Oh, okay. I'll do something. Yeah, just to think maybe it's here. Oh, no, yeah. Yeah. Again. Why you can Mhm. Yeah. Oh, yeah, I can. Okay, doesn't matter. So, these pulse discriminators are basically, I forgot. Oh, my God. Discriminator is uh, 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 comparators. Discriminator are these comparators, yes. Okay, yes. These pulse discrimination are basically an array of comparators done by with op-amps, as we saw in previous lecture. So yes, that's it. And at the end, we have some logic output when the amplitude of the input is in certain range. So this is very closely related to this here. Okay. Well, this part of a circuit is very closely related to this shaper thing because we can, for example, well, actually, it's something like this, no? We have some pulse that has some charge level. Well, what we correspond to some charge level, and then we have some shape with the amplitude of this shaped signal is corresponding to the pulse of the sensor. The very weak pulse is corresponds to the shape and height and the properties of this pulse at the end, no? And then this pulse can be measured, for example, with this pulse discriminator, where you define some level, two levels discriminator, and when the pulses here reach have certain level, we will have some output here. So, for example, this is a single channel analyzer. This is a single channel analyzer principle. So they work using this principle, no? So we have a well-controlled output from the detector after shaping, and we have some pulse discriminator tuned to some voltage amplitude level, and then we analyze that. Okay, so then we have some other property called the time walk from the signals from a detector, which is a dependence of the time measurement when we have some discriminator after shaper. So when let's say that we have some discriminator that is firing every time that the signal in the input cross this threshold. For a normal for a threshold discriminator, we will have a dependence on the amplitude or the shape of the pulse, or well, some time dependence of the pulse generated from the discriminator to the shape of the detector pulse. So depending on the amplitude, for example, we will have one signals coming earlier or later, and this thing is called a time walk. So normally we want to reduce this as much as we want. Well, we have some dependence like this. When the signal 8 is higher, the time delay is smaller, for example. One can fit some function to this dependence, and one can correct this, but if we don't have it, it's better. No, we can solve this by hardware. So one of the techniques used to assess this problem is the constant fraction discrimination, which function is based on instead to take some fixed threshold level, we take some fraction, fraction from the yes, one fraction from the input. So, and to do that, in the technique, there is a process which needs, well, we have some poles. Well, okay. Okay, well, this constant fraction is triggering with respect to some fraction that is defined by a circuit that we will see later from the input signal, and not depends on a fixed threshold. And to obtain that, we have to well, some steps. We need the original pulse that later is inverted and attenuated, and the original pulse then is delayed a little bit, and at the end we sum the delay pulse with the inverted pulse, and when we sum, we will have some signal like this, which will cross zero, and this zero crossing will depend on the fraction and some fraction of the pulse. This looks like this, and like in a schematic. Well, this is the schematic and how it works. So we have the signal, and then we have, well, the signal is divided into two. One part is delayed, the other is attenuated, but some fraction lower than one. And then it's inverted at the one that is attenuated is inverted here, and then sum to the delay original signal, and we get the zero crossing signal, and then we measure the time when the the signal after the constant fraction is crossing zero. So, and that is how it works. And I think that's it for today. Any question? We continue next time with more.
Which component and how it calculates the zero crossing?
Well, to calculate the zero crossing, you need an extra circuit. So you have the signal, which varied around zero, and then you have some discriminator. Basically, it's a normal discriminator here. So, well, we're supposed to have this zero crossing here, but since it's a discriminator, you can, for example, vary a little bit up, down this threshold. Is a normal threshold. And so
Okay.
this is not really a zero crossing, but some threshold level that you can vary. Depends, because you will have some well, this signal will be not perfect. You will have some noise here, and maybe you want to reduce or improve your noise rejection, just going a little bit up the noise level, for example, and you can vary this zero crossing level. Well, zero crossing level, you can not, it's not zero, but it's some threshold level to be more accurate. More questions?
And how do you take the fraction?
Well, the fraction, well, you have to calculate. I didn't put here.
Because somehow you need to have a circuit that this I cannot imagine how it's done. So-
Well, you mean in practice?
Yes.
Okay, so well, we have this question here that we have some signal. Well, this is the output signal. We have the voltage in the input, which is delayed. So the original input, which is delayed for some time. Then we have we subtract the voltage in the input at the same time, but with a negative. Well, with some constant. Constant attenuation factor, no? And that we do with op-amps. Yeah, for example, we can go back to op-amps. We can imagine with the different types. We have, let me see if we have something useful somewhere. Okay, for example, we can use well an array of operational amplifier. Okay, so we can have okay, let's imagine this. We can go back.
I'm terribly sorry, but I really need to run already.
Okay, it's fine.
Yeah, but please continue. Can you please afterwards upload this so I also can hear how we do?
Oh, sure, no problem.
Great, thank you very much.
Yeah, no problem. Okay.
Bye.
Okay, bye. Okay, what is okay, for example, here, first we have the stage where we split the two signals, no? And for here, we can have two operational amplifier that is fan in fan out, an operational amplifier here and here that take the original input and deliver exact copies of the input signal here and here. Then this delay is a cable. It's basically a cable, nothing complicated. And here, another operational amplifier, but with the amplifying factor lower than 1. So it's an amplifier made of an op-amp with a small amplifying factor. So in that way, you can exactly adjust your this factor here. But this is an inverted amplifying factor, but lower than 1, which is, I'll go quicker here. This is no. What is it? This one, no. So you choose some feedback resistor in this amplifier. And well, you have an inverted mode. Here you already have the inverted signal with an invert factor, and you choose a feedback resistor which is lower than the resistor in the input, and that's it. So that's how you create the attenuated signal and inverter. And what else? And then, yeah, that's in practice how it's done. And then to sum this, you also use another operational amplifier with some. Let's go back. Okay. Again, it's only that's why very important is you put. We don't have examples of this. I think maybe no. No, I didn't put. I think I will explain a little bit. Actually, it's a good idea to go over the stages of this one. But okay, so you use a operational amplifier like this that sums. Here on the input, you use sum the two voltages, and that's it. That's some. No, I will. Actually, it's a very good idea. Wait, next time I will explain this with operational amplifier how it works. It's a good idea to see it's a good example to see the a bit more complex application that we are very close related, and I'll be a good. Yeah. Okay, it's a good idea. Thanks, Waita. Good question. That's it. Something else?
No.
Okay, so thank you. See you later.
Thank you. See you.
Bye bye.